review a little bit more. Unit 2 is really large. You probably noticed. A lot of interesting information, but sometimes it gets mixed up in your head. So I'm going to try to keep solidifying that and go over our new content. So what is the symbol for the alpha particle? Draw them there. It's a little A, right? That looks like a fish. Okay? And then I'm going to note the charge and mass down here, but what are the numbers that go here and here on the alpha particle? Shout them out. Okay, 4 is the what? 4 represents the what number? The atomic mass or the mass number. So I'm going to put mass of 4 here. And 2 is the kind of its atomic number, but really it's, I'm going to say mass and charge of it is 0. We know the charge of an alpha particle is 0. Whose experiment used alpha particles? Shout it out. Rutherford, right? He shot alpha particles at gold foil. Now, an alpha particle, 4, 2. 2 is, I'm saying, the atomic number of alpha, but that's a lie. Who is it really the atomic number of? Helium, right? So another way to write that is a helium particle or nuclei like that. So you'll see it this way or this way. They mean the same thing, though. Okay, and then what can block an alpha particle? Paper, right? So paper is something very, generally meaningless as paper. It can block alpha particles. That's because alpha particles are so large, they can't squeeze through the atoms of paper. Because, paper is just a bunch of atoms together. They're so large they can't squeeze through it. All right, so beta particles. What do beta particles look like in the symbol form? Draw them in the air. See, some people saying B with the tail, okay? So you say B with a tail, and then what are the numbers on it? Huh? So where is the -1? On the top or the bottom? Bottom, and what's on the top? 0. So massive 0, and this one actually has a charge of -1. So you can say 0, comma, -1 for its mass to charge ratio kind of thing. And then what blocks beta particles? Huh? Not steel yet. Aluminum foil, okay? Something that's kind of more significant than paper, but aluminum foil isn't that crazy, right? Aluminum atoms are only so large, and so we have to use them to block the beta particles because they're a little smaller than alpha particles, so we need something more condensed. But another way to write this would be electron, the -1 and the 0. So it can be written that way or with the B. Okay, then gamma, what does gamma look like? Draw there. Kind of like a fish Y, like an upside down fish, like that. Okay, it can be like that or it can be kind of like that. It just depends on how fancy you get the curly part on the bottom. All right, does it have a mass to charge ratio? No, it's just straight up energy, people. It is just straight up energy. It does not have necessarily a mass or a charge. It's just gamma radiation. It's part of the electromagnetic spectrum, actually. It's kind of cool. And then since it's just energy can kind of get through pretty much anything. It can get through your skin, it can get through paper, it can get through aluminum foil, because it's wavelength. Speaking of wavelength, sorry, is gamma on the short side or the long side of the wavelength? Incredibly short. So short, it squeezes between the cells in your body and gets through your DNA. Right? Just like a lot of UV radiation, a lot of stuff can do that because it's just really, 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 really short wavelength. So what do we have to use to block it? Yeah. Lead block. Okay, so a lead block or a concrete wall, something like that. So what kind of, if you were a material scientist or you were trying to decide on building material for a nuclear power plant, your specialty is probably going to be in learning and figuring out what material can block gamma radiation and other forms of radiation, because you have to know how to build it appropriately to keep the community safe. Along with this, speaking of size, we all have seen the microwave. We've seen a microwave. Like the device, right? Not the wave. Okay. So we've seen the microwave. You know that mesh on the front? Why is that there?
So we don't get sick.
To what?
So we don't get sick and the radiation from inside doesn't leak out.
How is that great that the little holes on it? Because it's just like the front of the microwave has all those little holes on it. It's not there so the convenience of being able to see your food, right? You're like, oh, there's like the little dots on that thing so I can see my food. Great, right? Why is it really there? Like, what is the significance of those little holes they have? Right, so it's one to protect you from being sick from the radiation coming out, but microwaves, they're only so big, right? So if you make that hole just a little bit smaller than the wave, the amplitude of the wave can't get out. And therefore it stays in your in the microwave where it's supposed to be, and it's using all of its energy to excite the water molecules and make your food feel hotter. It doesn't actually cook the food. It just makes the food feel hotter because it gives it more energy. And that's why it's smoking hot when you take it out. So the microwave is too big to fit through the hole, so therefore it does not escape. That's kind of cool, right? There you go. Okay, so let me briefly talk about the decay equations because we know what these particles are, and then we're going to stop and go over our quiz. Okay, so if you're decaying, if you are an isotope of carbon, carbon-14, you decay by beta decay. That means you carbon, what's your atomic number? PR table? 6, okay. You decay by beta decay. So you are decaying, you're making beta particles and something else. But beta particles are labeled B, 0, -1. So you're making a beta particle through your decay process. And then your second product is actually a new atom. It's a totally new atom because the way that the balancing of these nuclear decay equations work are the masses must be conserved due to the law of conservation of mass, right? So what is the number that's going to be on this top one over here?
14.
Because 0 plus 14 is 14. Okay, the lower numbers are representing the number of protons, and we're going to say the protons kind of stay constant as well, just they change form. So what number has to be over here to equal 6? 7. So now your job is to say, who is that? According to the periodic table. Nitrogen. Okay, so that's a nuclear decay equation right there. We're saying that carbon-14 is so unstable, it goes through beta decay and it transforms or transmutates. What does mutate mean? Change, that's it. Mutate means to change. Mutate your DNA, changes the genetic code. Mutate an element, changes its identity in this case. So carbon-14, so unstable, goes through beta decay and becomes nitrogen-14 because it's more stable. That's kind of cool, right? So, but we are totally defying the one rule we said we would never change. We're changing the number of protons. In this case, we have 7 protons versus 6. And that's because it's called nuclear decay. So what's decaying? The nucleus. And what's in the nucleus? Protons and neutrons, right? So now we had all this big discussion about electrons. Now we're going to hit this one little bitty topic on what can we actually do with protons and neutrons. All right, so let's do this one. Let's do I-25. Iodine 125 decays by alpha decay. What's the iodine atomic number? 53, thank you. Okay, and it decays by alpha decay, so what do you want to write here? Say again? The A thing, 4 and 2. Okay, so 125 equals 4 plus what? 121. 53 is equal to 2 plus 51. Who is atomic number 51? SB. Antimony? SB. Okay, so explain to me, like I was explaining to you up here, explain to me what iodine does. Hayden, explain to me in words, not chemical symbols, what that means. Somebody. Yes, this is 2 protons and 2 neutrons, but here I'll explain this one again. Carbon-14 is unstable. Its nucleus is unstable. Therefore, it undergoes beta decay and transforms or transmutates into nitrogen-14. Okay, somebody else. Zachary.
So when you're asking what it does, are you saying what's happening to it or what the element is used for?
I want you to explain to me what happens in the nuclear decay process, like I just said in the sentence about this one. I just put that equation in a sentence.
Yeah. So it's losing 2 protons and 4 neutrons in the form of nucleuses that are being ejected from its nucleus in order to have a form that is more stable. And those nucleuses are helium nucleuses, so you can write it as He.
Okay, so that is unstable. Iodine 125 is unstable, and through the decay process, it becomes more stable to the antimony 121.
Yeah.
Okay, so the goal here, you heard me say stable and unstable, right? Why? This doesn't just happen for kicks and giggles, right? Why is it happening? All right, so this is an unstable radioisotope. Unstable radioisotope. What do you think radioisotope means? It's not a radio wave, right? It's radioactive, maybe? It's radioactive, it's able to decay. So an unstable radioisotope, which is just a radioactive isotope, is decaying to something more stable. and it stops at that stable isotope, whatever it decays to. And the whole thing they're talking about being stable is, do you remember that protons and protons, they live in the nucleus together, right? Do they like to be right next to each other? No. Protons and protons are pluses and pluses and pluses and pluses. They repel just the same as electrons repel. So this one right here probably has too many protons or too many neutrons in the middle, and so they're going to kind of transform into a more stable form with a better nucleus. This one too. This one probably has too many protons in the middle of it. Therefore, it's ejecting protons, like Zach was saying. It ejects protons to ensure that it becomes more stable as antimony 121. So that's all this is. We're just talking about more about the nucleus versus the electrons. Yeah.
Whether you add or subtract it, is that based on like if it's beta or alpha?
Yep. It's all based on the type of decay, and there's 3 types of decay. The only 2 we can use in terms of balancing the equations are alpha and beta because they have numbers. Gamma, like this one right here down the bottom, 56, nickel 56. What's nickel's atomic number? 28. Okay, it decays via gamma radiation, 0 and 0, because it has nothing in terms of mass or proton number. So it stays a less energetic form of nickel 56. It actually doesn't change its nucleus whatsoever. It doesn't change its mass whatsoever. It's just a more stable, less energy form of it. It's just less energetic. But every form of radiation actually does give off that kind of gamma radiation. Okay, so let's halt on nuclear for a second, because we have actually gone over a lot. There's not much to this part of the unit at all. Let's look at our our quiz real fast. I only want to go through 2. Okay, everybody work with me on this one. Okay, if you got 100, then this was surprising. I did not know. According to problem set 5, it looks like everybody's like hunky-dory, knows exactly what's going on with electron configurations. It's because some people think they're dishonest with themselves and with me, but homework is kind of a completion grade, so you got to help yourself. And the problem set 5 key is posted along with problem set 4, along with problem set 6, if you have questions that you were just, for some reason, are not asking. Those keys are posted on my website under Unit 2 documents. All right, what was the first one I gave you on the quiz? Chlorine? Okay. I think actually the chlorine one was easy, but I will go through it. Whenever you're looking at your periodic table, you simply are going across the periodic table. So 1s2, remember helium actually does belong over here. So that's 1s2, 2s2 because you go through lithium and beryllium. 2p what? 6, and that means you're all the way to neon. Okay? Then you drop down to 3s2, 3p what? 3p, yeah, 5. Why are we stopping at 5? Because chlorine doesn't have 18 electrons, it has 17 electrons. So that 2 plus 2 plus 6, that's 10, plus 2 plus 5 is 7, so that's 17 electrons. So you actually can double check by counting the electrons. Now, if chlorine formed an ion, it's going to gain or lose electrons. Is it easier for it to gain or lose electrons based on its location on the periodic table? Gain. So what ion would it form? What ion? Chlorine is still chlorine. Do not change its name. Chlorine with a what charge? 1 negative, right? And that has the appearance of argon, but we all know it's not argon. It's just got the same electron configuration of argon. And electrons, they don't define the element. What defines the element? Protons, right? So chlorine is this. Chloride is blah, 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 3p6. And 3p6 indicates it's the same as argon. So that's kind of interesting. Some of us were writing argon with like a 1- charge. Nah, argon doesn't not. Argon's not even in the picture, okay? It's just the electron configuration of chlorine looks like that of argon. All right, on the bottom, there was one with, was it indium? Ion. What did I get to on the bottom? Sorry. SN, sorry, I changed it from class 3 to class 4. So 10, 4 plus. All right, so this one's a little longer, so you had to go through blah, 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 all the way down to 10, right? But I need to do blah, 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 because I'm assuming we know what that is, but sometimes we don't. So you guys tell me, 1s2, 2s2, 2b6, 3s2. Okay, stop there. We're here. We're at calcium, 4s2. When you hit D block, what is the rule? N minus 1. D block starts at scandium and goes to 10. So that's not 4D, it's 3D, 10. And then you're stopped. You're out of D block. Now you're going to enter P block, and now what happens? Go back up to 4P6. And so that's 3D10, 4P6. Back down here. 5S2. Okay, again. 4D10, thank you, because we're going to make sure we're accounting for the D block. And then we're all the way over here, we're to 10. You can see it's 1, 2, right? 2 and 2, what block? P block, but it's 5P2. Right, so we probably saw 10 went all the way there, but then some of us forgot to go back and say, why is that 4 plus form for 10? Well, that 4 plus is just the loss or gain of electrons, first of all. Loss of what electrons? Valence electrons. And if you're losing valence electrons, that means you have to know what the word valence means. What does that mean? The very outside energy level, and which is that? 1, 2, 3, 4, 5. 5. That means the fifth energy level loses its electrons, which are where? Where do those electrons exist in this electron configuration? 5p2 and 5s2. See, 2 plus 2 is 4. 4 electrons are lost. Boom. That's awesome. So this is no longer there. It should go blah, 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 4p6, 4d10. Stop there. It's just your knowledge of what valence is. I think that's the only part we messed up there. Okay, that's all I'm going to go over right now, but I wanted to do those 2 examples because they were kind of all-encompassing. If you did the noble gas electron configuration of this one right here, what would be the noble gas electron configuration really quick if you had to, noble gas shortcut, if you had to rewrite that? Who's the last noble gas you pass before you get to chlorine? Neon. So you go neon, and then you continue as what, and what? Neil, you're sitting right there. As what? 3s2, 3p5. So looking at this right here, you don't even have to look at the periodic table. How many valence electrons does chlorine have? Looking at this right here, how many valence electrons does chlorine have? How many? I hear you. 7. This number plus this number gives you the valence electrons of chlorine, because that's the valence level, right? The third energy level. How many electrons are in there? 2 plus 5. That's 7. You can also look on the periodic table and go, oh yeah, totally, it's in the 7th group, it's got 7 valence electrons. But you should be able to tell from the electron configuration as well. So you have lots of tools, but if you don't know how to use them, we're SOL. Okay, so let's talk a little bit more about nuclear, and then we have an activity we're going to do together. So I have a couple of things I want you to write down for nuclear. It's not very much, because you guys write this on your reading guide, so that way all your stuff stays together, because some of the stuff is in your reading guide and I'm not going over it. Okay, so your reading guide, you're writing down your notes on it, because I'm not going over everything on nuclear. Alright, so I'm going to talk briefly about this, and then I think really the only highlighted parts and some of the things I circle are the things you should really write down. Okay, so we know that Dalton said all atoms are conserved. He said, and that was true. But he didn't really talk about the rearrangement all the time. He said that everything's the same, which is not true. So one thing that we need to know that he said, which is false now, is that atoms are unchangeable. They are what they are always. But we just said that atoms, aka isotopes, are radioactive. I'm not going to sing, but I really, really want to. Okay. So isotopes are radioactive, which means that they will decay. Okay? So if they are decaying, that means they're changing, mutating, transmutating, whatever word you want to say. So Dalton's theory was disproved with nuclear chemistry. Secondly, there's a reason why. There wasn't just like, you made this observation. You're like, okay, I accepted all atoms are going to change. There's a reason why. And what was that whole, we emit energy to do what? What was my purpose of going over that in the beginning performa? Everything's got to become more stable, okay? So as you emit some sort of nuclear decay particle, you're also always emitting energy. So why are we emitting energy? It's because everything will become stable after it's released its pent-up energy. So that's kind of the theme here. Everything's decaying because it's unstable. We want it to become more stable. So there's not a whole lot you're writing there, just the top and the bottom. I'm explaining a little bit more between. If you're a writer, you're not going to like them today, so I'm going to keep going. Okay, so radioisotopes, we just explained what they were. They're isotopes that undergo what? Say it for me. What do they do? Isotopes that decay, okay? That's because they're unstable. So pretty much every single isotope is radioactive. All but 17% of them, okay? Only 17% of isotopes are actually naturally stable. So everything we talk about, actually this relates to, because everything is going to naturally decay. Americium, whatever it is, americium 200, americium, I don't know if your table is, whatever it is, americium X is in our fire detector, smoke alarm, and it's something that will naturally decay if it's exposed to certain chemicals, and then it actually causes something to happen in the smoke alarm and make it go beep beep beep, and there's an alarm. It's naturally decaying all the time. You have things in your body that are naturally decaying all the time. Carbon-14 decays to carbon-12, for example, and that's how they can track sometimes relative dating versus actual radioactive dating. Okay, so we just talked about that decaying. Anything that's unstable will decay. Okay, so we also talked about this in our first part. How many protons and how many neutrons does a alpha particle make up? Or what is it made up of in terms of protons and neutrons? 2 neutrons and, look right here. What does that 2 represent? That represents 2 protons, and what does the 4 represent? Its total mass, which is 2 protons plus 2 neutrons. There's the only 2 things that are making up the individual masses. And then, like we kind of just talked about this already, the atomic number is changing in this process, and you're like, oh no, we can never change the atomic number. In normal chemistry, we won't. In nuclear chemistry, we are allowed to. So radium, Ra is radium 226. What's the atomic number of radium? Get your periodic table out. It's on the lower corner near francium. 88, okay. So radium 226 decays to radon 222 and an alpha particle. And radon's number is it's 86. So you can see from 88 to 86 the nucleus atomic number did change. So it's just one more example for you. And if you did a good job in your reading, guys, then you're like, I got this. Majority of the rules, most of us look pretty good here. All right, beta. This one is so the last one was kind of like a heavier particle, last particle. This one's a high energy electron, right? And we already kind of went through this because the high energy electron is represented as an electron form like this. It does have a negative charge, but what's actually happening is there's too many neutrons actually in the nucleus, and that has made that nucleus unstable. So it's really weird how it does this, but it takes a neutron, which is neutral, it pops out an electron, and it keeps a proton. So it's kind of what it's kind of saying is a neutron is an imaginarily combined proton-electron combo. That's kind of what it's saying, but it's actually not. It just helps you make sense of how in the world does a neutron become a proton-electron? Well, they kind of counter each other, so it makes sense. It's neutral. But what's actually happening is the neutron is morphing itself, ejecting a proton, and leaves behind a proton. And that's how it helps the nucleus become more stable. And that little piece of information is not that important. I just want you to know how to write the nuclear decay equations. So iodine 131 decays to xenon 131 and a beta particle. Oops. So that one's thumbs up. A lot of this is repetitive right now. Not a whole lot of new stuff. All right, so what's next? Gamma. Straight up energy. Nothing crazy, except for the Hulk. Okay? and it's actually going to be present in every form of nuclear decay. So it will accompany all forms of nuclear decay. But it doesn't affect the proton number, doesn't affect the mass number. It only affects the stability of the nucleus because it releases excess energy. So that's kind of nice because we don't have to write a whole lot in terms of nuclear decay equations for it. And it is incredibly small in terms of its wavelength. We're almost done. We need like 3 more slides. So what was that word I kept saying that told you it changed the nucleus? Changed. I said, what is this? Mutation, right? So transmutation means that it's transforming, it's moving from one thing to another, that as that process occurs, it's changing itself. So transmutation is going to occur by nuclear decay, which is kind of our theme today, so that makes sense. And definition, if you want a more definite definition of transmutation, is that it's changing from one type to another. So that's kind of like it transmutes across. That's how those two things come together. So the cool part is that transmutation, we can force it to happen. Who's ever heard of the Hadron Collider or the particle accelerator? Okay, so it's basically a humongous racetrack underground in Sweden. We can go on a field trip. Okay, it's in Sweden, and they pretty much fling atoms around this humongous racetrack underground, and they make them rotate around in opposite directions in hope that they will collide. So it's called the atom snatcher, or the Large Hadron Collider, because they smash, element A or atom A into atom B, and in this collision, it should fuse the two nuclei. So if you take one atom with 2 protons and the other atom with 3 protons, and you smash them together and they collide together and they fuse their nuclei, what have you just made? What's the nucleus made of? I said 2 protons and 3 protons. 5 protons, which is who? Boron? Boron, okay? That means I just told you I took helium and lithium and I fused them together to make boron. That's really cool. Now, you know the periodic table has all this empty space. I'll look over here. We got unlithium and propylium. I don't know what they all these other things are. Unnitrium, septium, adamantium. Those are like placeholders. Those are not real things right now. We've not made them. We actually just made, like last year, made fluorbium and livermorium, which are these two down here. But if I took something like fluorbium, whatever, and I atom smash it with livermorium, or atom smash with something smaller, I can make something bigger, which is kind of cool. So that's actually a way that we can fuse nuclei. It's somewhat impossible. The reliability of atom smashing is very, very, very small. But they also have found that there are other particles that fly around with it called neutrinos, which can travel close to the speed of light. So it's a bigger field than just atom smashing. Yeah.
I could be wrong, but I think they got a few atoms of uninoxium recently. I think it was when I was in 8th grade, because I remember my teacher mentioned.
They could have, but if they decay,
Yeah,
and they can't repeat the trials, yeah, because they rely on peer-reviewed journals to make sure that they can repeat the process. Like somebody published that they found cure for cancer or something like that, and then they had lied to get funding, and so they had to do peer review process, and they said if they couldn't repeat it, then it didn't exist. So, but that could very well be possible. I'm not up to date on that. Okay, so last topic we're going to talk about, fission and fusion. Which one means come together? Fusion. Which one means go apart? Fission. So fission goes apart, fusion comes together. I'm not explaining much more than that except for some applications of it. So those are 2 definitions you should know. Nuclear fission pulls things up, the nuclei apart. Nuclear fusion puts the nuclei together. So different applications of it. We know that we are able to get nuclear fission to release large amounts of energy in nuclear power plants. So you need to know fission is what we employ in power, energy, making energy for us. Nuclear power plants. And I do have Springfield nuclear there. fusion is what we hope our sun never stops doing, because the fusion that's occurring inside the sun, helium nuclei or hydrogen nuclei fusing to make helium nuclei, we hope that never stops, because as that occurs, it's fueling the sun to make radiation, solar radiation, and also releasing large amounts of energy, which we feel, right, on our skin, and it keeps us warm. If this ever stopped, nuclear fusion stopped from the sun, we would have no sun, therefore no life on planet Earth. Right? So we cross our fingers that doesn't stop for a long time. Okay, so energy applications is fission, solar radiation is fusion. It comes from fusion. There's not really any other applications. There was this like 17-year-old boy I saw on TED Ed that learned how to make fusion happen, like a little contraption about the size of a backpack, and he was trying to get energy out of it. And it was actually applicable. I was like, what was I doing at 17? Not saving the world. Okay, so that's what we just talked about. Okay, let's do a radioactive decay example, maybe 2, and then I want to move on to that. We'll move on to our next activity. So far, so good though. Do you remember a lot of this information? Have you ever heard of nuclear chemistry before this class? Some of us haven't. Okay, so this is a very small piece of our chemistry though, so that's why I'm moving through this one. All right, so this is an example of radioactive half-life. What is the definition of half-life? What is it? All right, so it's just a time. Half-life is time. So carbon-14's half-life, the radioactive isotope carbon-14, its half-life is called T1/2, is how we like to label it. It's 5,730 years. So that means in 5,730 years, of the entire sample of carbon-14 we have, half of it will have decayed, half of it will still be carbon-14. Well, then if I allow another half-life to pass, another 5,730 years, another half of that remaining carbon-14 will have decayed. But after 2 of those half-lives, if half decayed the first time and another half of that remaining decayed the second time, what total amount has decayed? It's half of the remaining. So I'm going to show this. If 100% decayed, that means only 50% of carbon-14 is remaining. Say you started off with 100% of carbon-14. Half of it decayed, that means you're remaining, you have still carbon-14, that's or 50% of your original sample. If half of that amount decayed, you're left with 25% of that carbon-14, and then how much of the other stuff? 75% of the other stuff. So if I had 100 grams of carbon-14 and one half-life passed, how many grams of carbon-14 do I have remaining? 50. And then if I allow another half-life to pass, how much carbon-14 do I have remaining? 25 grams. If I allow another half-life to pass, 12.5, and it goes on and on and on. So it's called exponential decay. You've seen a graph like this. Okay? Exponential decay, like in math, right? And so I'm not going to go into the mathematics of it, but if this is grams of carbon-14 that you had originally you just told me we had 100 grams of it. And after the first half-life, ooh, that's way too low. After the first half-life, about here, that's called T1/2 or T1/2. So that's about 50% of it remains. After the next half-life, another 50% decayed. After the next half-life, another part. So it eventually goes down so close to 0, it looks like 0% of the carbon-14 is remaining. But you're never going to be able to get to 0%. It's always going to be a teeny part left. All right, so that's the kind of concept behind it. So if we had to approach a problem like this, you're going to be given a starting point in grams. You're going to be told usually the half-life. And your job is to figure out how much remains or how much doesn't remain. So carbon-14 emits beta radiation. Okay, that's cool. Its half-life is da-da-da. Assume you start with a mass of 2.00 times 10 to the negative 12th grams. How long is 3 half-lives? So first question doesn't even pertain to the mass. How long is 3 half-lives? You have a calculator? 5,730. So what is that? 16, 17, 20? 17,190 years. Okay, so first question is done. It didn't even require chemistry knowledge, right? How many grams of the original isotope remain at the end of the 3 half-lives? So I'm gonna write this down here. Ignore this for now. I'm not gonna go into like PERT stuff. So 2.00 times 10 to the negative 12 grams. After one half-life, I like to do it linearly. After one half-life, how much remains? Half of that, right?
Yeah.
So you can do it in your head. What's half of that? 1.00 times 10 to the negative 12 still. Okay, it's still a really, really tiny number. So this is before decay started. This is after one half-life. After another half-life, how much remains? Okay, so 0.5 times 10 to the negative 12 is 5.0 times 10 to the negative 13, because I took the decimal back one. So that's after the second half-life. Okay, after the third half-life. So 2.5 to the negative 13 grams. That's the final answer. If I know how many half-lives pass, I can do it linearly, like very easily, versus plugging into a formula. If you did want to plug it into a formula, you would do 2.00 times 10 to the negative 12 grams times 1/2 to the third power, which is the number of half-lives that passed. So if you're mathematically minded, you'll take your original mass times by 1/2, raised to the number of half-lives that you passed, and that will give you this. Same thing. I'm good at dividing by 2. I don't know if you guys are, but I'm good at that. Like, I could win some sort of dividing by 2 competition. Okay, I'm sure you could too. Everybody can divide by 2. All right. So this one, tell me how you would approach this one. Magnesium 56 is a beta emitter with half-life of 2.6 hours. What is the mass of manganese 56 in a 1 milligram sample of the isotope at the end of 10.4 hours? What was the first thing we did in the last problem? Figure out how many what? How many half-lives have passed? 10.4 hours divided by 2.6 hours, which is the half-life time. This is the total time. You guys, can you do that in your head? 4. Okay, 2.6 times, so 2.5 times 4 is 10, right? So 2.6 times 4 is an extra 0.4. So that's 4 half-lives. All right, that's cool. What do I start with now then? I have a 1 milligram sample, and that's before the reaction, before the decay occurs. After the first half-life, how much do I have? 0.5 milligrams. After the next half-life? 0.25 milligrams. Next one. 0.125 milligrams. How many half-lives have passed so far? 3, I think, right? So here's the first half-life that passed. Second half-life happening. Third one right now. Fourth half-life? Milligrams. There you go. That's how much is remaining of the original manganese 56. That's how much is remaining. So the rest of that, like 0.9375 grams, the rest of that has decayed to whatever manganese 56 decays to. That's the other part of it. All right, thumbs up if you feel you're okay on this. And we will practice more tomorrow. Okay? So let's get up. I need to tell you something fun we're going to do. Let me make sure I've got, okay, cool. We're going to play a game called Atoms. And it's called Atoms, right? Did you see the periodic table? We have all these atoms we go with. And this is something I just made up, and I want you to give me feedback if this is something cool, if you like it. And basically, it's bingo. But you're going to have movement. You've got to walk around. So the rules of the game are you must get 3 atoms, okay, bingos, okay? ATMOS, 5 letters, bingo, 5 letters, you get it? Okay, cool. All right, so it's like bingo, but you must get a bingo across, diagonal, and down. You have to get 3 bingos. And each of these requires you to talk to somebody else. No person will talk to the same, you only talk to, you'll talk to one person per question. So if I was a partner right now with Rebecca, and I would say, okay, can you answer one of these on there? And she's going to pick the one she's really good at, and she's going to answer that question for you. You have to do a quick, brief summary of what she says. It could be a 1 word, it could be 5 words, it can be something really brief. And then she's going to initial the question that she answered for you. And then she's going to say, okay, Ms. Miller, can you answer one of these? I'm like, okay, I can do one of them, only one. And then I'm going to answer a question for her. And she's going to write down that briefly, and then I'm going to initial her paper. once we've initialed each other's papers, we did our job, we traded answers, we go on to another person. So you're only going to have one person's initials on here once. Okay, she can't do like 5 of my questions. Right, but now that I've learned something from her, I can answer that question for somebody else because I'm knowledgeable, you know, I've gained that knowledge. So you can write on these papers, you can write answers in the back if you want to, but your job is in less than 30 minutes, you must get at least 3 bingos. Does that make sense? Okay, if it doesn't make sense, the instructions are on the paper. Preferably, please initial in a different color than pencil. Pencil is the color now. I can't see black. I can see black on here. It's hard to see pencil on here, so I want to make sure that you're good there. So I'm going to let you set you free. You need to get 3 bingos, okay? And there might be extra credit involved. Go. There might be extra credit involved. This is your paper. You can start with the person next to you if you want to.
Can we answer one?
Write down their response. Okay, I'm going to interrupt you real fast. 2 things I've seen already. Ready? Yes, please use your notes. So if she asks me a question, if Emma asks me a question, I'm like, oh, hold on, let me look this up in my notes for class. But as I tell her, she's writing down my response on the back of her paper. I am not writing down my response for somebody else. That's lazy. She's going to listen to me and she's going to go, okay, I can done this down to like 3 words. Boom, 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 there. Okay, do not write the entire version of the response. That's probably just still talking on things. There, just full of knowledge. Okay, so.
So, also what happens is, you'll pick a question to answer, and then I'll write down. So from what I was going to say, there's a couple of 3 chance to put like together.
Get up and move around. Get up. Go visit other people.
And so when you balance it into your thing, you have to like it starts unstable and you have to do the motion to hit for carbon. What else?
That's the same as you said. Sorry.
So it starts unstable and you have to balance to make it stable. Yeah, an example is carbon 14 to 0 and negative 1
Yeah?
Can you tell what kind of atom, what element is close to
Just feel like
Or blood.
Oh, wait, that's hot. I'm finding out stuff from you guys. Be strategic about your questions. Ask across and down and diagonal.
I'm gonna